Yeah, today I want to present one of the results stated last week by Sam. And so the reference for today's talk is essentially a paper with the same title, Lagrangian chaos and scalar advection in fluid flow by Bedrossian, Blumenthal and Sam. And so we have one of the authors here. So if you have any doubt or questions, feel free to ask also Sam. And okay, let's start. So as Sam explained last time, the goal is to understand, to study Lyapunov exponents of random vector fields, and random here is the keyword. Coming from fluid models. Maybe let me start by recording the main fluid model we want to consider. I'm going to consider the two-dimensional Navier-Stokes equation with the random force term. And this is the equation. Let me explain the Lagrangian condition. And initial condition is not given space capital H. H is a space of vector fields. So so first of all, I'm working on the two-dimensional setting. The two-dimensional torus. And so the main term here, so this is just 2D Navier-Stokes, and this is the stochastic term. And let me call it F for a second. And about the structure, let me just recall a couple of things. So first, this term is nothing but a base of L2 vector fields over the torus. Those are coefficients. QK are coefficients with some decay, say k to the power minus alpha, and alpha is some number, big enough, say 5. And second point, the space capital K appearing here. This is the set of modes where we are adding the noise. And we want to assume that K is not degenerate. So if K were empty, this is just standard Navier-Stokes, and we are not able to prove any result. So we need to assume that in a certain sense K is big, and I will be a little more precise later on. So K is kind of big in some sense. And yeah, W is nothing but W, K, T. Those are independent inner processes over some probability space omega sigma. That's the picture as explained last time by Sam. This has to be understood in the mild formulation. And let me say something about well closeness. So here we are adding a force. In time it's quite rough, but in space this force is very regular. So I'm assuming huge decay of coefficient QK. So in particular, we can consider as a natural space to understand this problem, the space of vector field H sigma d, vector fields with zero divergence, regular, and this is the regularity parameter, and I'm going to assume the regularity parameter is, of course, related to the parameter alpha. Natural inequality to require here is something like. So given alpha bigger than 5 and sigma in this range, one can prove existence and uniqueness of solutions in a class like continuous in time H. Solution. And when I say solutions in the space of continuous vector field H sigma in time, I mean that almost any sample belongs to this space. So this is true with probability 1. Okay, so in particular, every vector field I'm considering is very, very regular in this talk. Okay, one can consider also other models, and as mentioned by Sam last time, one can consider Stokes. One can consider just Stokes, or the finite dimensional version of Navier-Stokes, so the Galerkin approximation of Galerkin. And the advantage of working with these two models is that they are essentially finite dimensional. And this, I mean, helps improving a couple of things, and I will explain later where finite dimensionality can help. Okay, just to recall some notation.
Out of curiosity, so if I look at these Stokes or the Galerkin, is it the same? Do you face the same issues more or less, except for some technical things, or is it really?
I think it's yeah. The proof is really the proof of positive Lyapunov exponent, which is the main theorem I'm going to state, is very different. When the system is finite dimensional, you can apply Faustenberg theorem and get an invariant structure. And to rule out the invariant structure is enough to apply Hormander theorem.
Yeah.
In the infinite dimensional setting, Hormander theorem alone is not enough.
Okay.
You have to do a lot of work, and I try to explain.
That's probably what you're talking about today.
Exactly.
Okay.
Okay. Good. So yeah. Let me recall a couple of. U bar is nothing but the vector field ut, T positive. It's the solution of my Navier-Stokes equation. And just to be clear, U depends on, of course, time, space, and omega, which is because it is random vector field, and omega belongs to our fixed probability space, capital omega.
T bigger than 0.
Sorry?
T bigger than 0.
You are right. T bigger than 0. Yeah, correct. Thank you. And okay, given such a solution, we can define the Lagrangian process, which is nothing but the flow map associated to U. But wait, X. And we are interested in Lyapunov exponents of this flow map. So more precisely, we want to study the following quantity. We want to study the exponential stretching for the linearized flow map. And I can state the main theorem. Recall, it has been already stated by Sam last time. Let me call it the theorem 1. The theorem says the following. We can find a constant, lambda plus, positive, and I want to stress that this is a deterministic number. This is not a random variable. such that the following identity holds. We can pick any initial condition in our class H sigma d, any points, and if we compute the limit already written here, we get exactly lambda plus for any point, for any fixed point, and with probability 1. And actually, we can prove a little stronger result. So this is telling us that with probability 1, there is at least one direction that grows exponentially. Actually, one can prove that any direction grows exponentially. And let me call it the theorem 2. Maybe. Okay, pick epsilon very small compared to lambda plus obtained in theorem 1. Pick a point in our two-dimensional torus, a direction in R2, and the initial condition. Then we can find a random constant C depending on epsilon x v and the initial condition. This is random, but it is almost surely finite and positive. And given this constant, we have the inequality okay, sorry. Omega t bigger than this constant C, this random variable C, exponential of lambda minus epsilon, lambda plus minus epsilon. So the linearized, the gradient of our flow phi grows exponentially fast at a rate which is a little slower than lambda plus, starting from an initial condition. So in particular, if we apply if we consider the transport equation, some good initial conditions, say, it is, well known that the solution of time t is obtained by taking the composition of f with the inverse of the flow map. So if we want to study the growth of gradients for solution to the linear transport equation, we can apply this result. Actually, to be a little careful, because here I'm applying the result to the inverse of the flow map, but the conclusion is the same. What we get is that the gradient of ft in any LP norm grows. So here we have again a random constant, but still it grows exponentially with some lambda, say, with probability 1. Okay, so first theorem is growth of the modulus of the gradient of the flow, and the second theorem says that actually any direction grows. And I'll be talking mainly about theorem 1. And the idea to go from theorem 1 to theorem 2 is to use some ergodicity of a certain process, the so-called projective process, and then gonna explain it maybe later. Okay, let us focus on theorem 1. 1, 2 first. give a very rough explanation of how proof goes and try to enter into detail in some parts of the proof. So let me write plan of strategy of proof. There are essentially two steps. The first step, let me call it rigidity step. And here I'm going to show two things. First, thanks to the ergodic multiplicative theorem, we can find existence. We can prove the existence of the limit, because a priori it's not even obvious that the limit exists. And it's not, of course, obvious at all that the limit is a constant. So this gives existence, at least existence of the limit. And the second step is the Furstenberg. So the second step in this first rigidity step is the application of Furstenberg type theorem. And this says that if the first Lyapunov exponent is equal to 0, is not positive, then some deterministic rigid structure occurs. And this deterministic rigid structure is preserved by our system. So some preserved deterministic structure appears. Okay, this is what concerns rigidity. And the second step, in the second step, we want to use properties of our SD to show that this rigidity cannot occur under certain assumptions in the case of solutions to the Navier-Stokes equation. So rule out rigidity. And once the rigidity is ruled out, so there is nothing. I mean, we have a positive Lyapunov exponent and all the other results. And so let me stress that the first part, so in the first part, one can consider a more abstract setting, and probably I'll consider a more abstract setting, the setting of RDS, and one can state all the theorem in this setting. And while stating this theorem, we collect all the assumptions, and at some point we want to show that our concrete problem, our solution to the Navier-Stokes equation, actually satisfies all of these assumptions. And this will be part of the second step. So this is about the Navier-Stokes, and this is actually quite general.
So yeah, when you say you rule out the structure, then do you get a quantitative estimate? Do you get a good quantitative estimate on the lambda, on the Lyapunov exponent?
Don't think so.
The way you phrase it, it looks like it just says it's positive.
I don't think so. Just lambda is positive. Good.
It's obvious that it's not negative.
It is obvious.
Is it obvious that it's not negative because you're saying it's either 0 or it's positive? So
yeah, the point. So I mean, it's part. If it is, let's say, if it is smaller than 0. Yeah, this is the biggest Lyapunov exponent. What I want to show is that there exists at least one which is positive.
Right.
Okay, and this is the biggest, and this will be positive.
Okay, but they sum to 0.
Exactly. So maybe the correct way to write, I mean, don't know what's given this. Let me.
If it's obvious that it's not negative, then it's fine.
Yeah.
It wasn't obvious.
So, I mean, either they are all 0 or there is one which is positive. And here I'm staring at the biggest one. So, okay. Yeah, I mean, this is, I think, a good comment. Given that our vector field is divergence free, the differential of our flow map as determinant 1, and this in particular implies that the sum of Lyapunov exponent 0. But maybe now I'll give the statement, part of the statement of the multiplicative ergodic theorem, and I will say something more.
Say it in terms of one of the top and the bottom are very quick, at least for
correct. Yeah, one way to state this one is when the biggest eigenvalue and the smallest eigenvalue are equal, then you get rigidity. Okay. Let me very briefly recall the abstract setting equal to +1 by SEM, the setting of random dynamical systems. RDS framework. So let us consider capital theta as a map from H. I'm going to denote by H the space H sigma div, so our space of good divergence-free vector fields. So we consider this map from H times the two-dimensional space, and H times the two-dimensional space is going to play the role of our phase space in this part. Sometimes I'm going to call it Z, phase space. And we have a natural action given by the solution of our Navier-Stokes equation, which is defined as follows: pick an initial vector field and an initial point x naught, and we get qt, the solution of time t of our Navier-Stokes equation, and what I denoted by xt, which is nothing but the flow map associated to ut, starting from the initial condition x naught at time t. And this is a random dynamical system in a sense that, well, we have a flow acting on a phase space, but here we have the dependence on this parameter omega, which is the random parameter. And again, there is a probability space sitting over there. And the key property, which will be fundamental, the following. The key property is the following. The so-called cocycle property, which has been already mentioned last time by Sam. And we assume that if we look at the flow map, if we look at our random dynamical system at time t plus s, then starting from some, say, then this is equal at the same random dynamical system starting going all the way to time s and taking the composition with dynamical system going all the way to time t. But here I need to shift a bit according to, I have to shift a bit the random parameter omega, and the shifting here, theta t, yeah, correct, theta s. Yeah, I should match the time. Yeah, theta s is a flow in omega. Preserving the probability. And so if we consider the concrete realization of omega in terms of continuous path and the Wiener measure, this theta is nothing but the shift of factor s, just moving the time parameter of the curve. And given the second fundamental property, which is true in our setting, is the fact that these two terms are independent. And this comes from the property of the Wiener process that we call independent increments. And this is fundamental to get the Markov process out of our Lagrangian process utxt. This is key in what follows. And given this random dynamical system, we can associate very naturally to it a linear cocycle. So in our case, the linear cocycle is the one giving rise to Lyapunov exponents, so the differential of the flow. Let us denote it maybe. Let me use this more general notation to denote the cocycle. So in general, the cocycle is a map A, random map, sending our phase space Z, or if you prefer H times the two-dimensional torus, into matrices. And for our applications, we care about SL2. And the key property, our concrete cocycle is simply given by the differential of the flow map at time t. given a solution U to the stochastic Navier-Stokes equation. And the key property here to keep in mind is again a cocycle property, which says the following. It says that, again, if we look at our cocycle at time t plus s, then we can consider the cocycle starting from the same random path, going all the way to s, and keep the composition. And this time, there's not really a composition, this is a matrix multiplication. And here we have, yeah, maybe I should be a little more precise. I should add here the variable ux, which is the point in our phase space. And here what I get t, and I get again the shift theta s of omega. And here I get us xs. Okay. So again, same cocycle property, and again, a very important fact. In our setting, these two matrices are independent. And if you want, you can think of this linear cocycle as a kind of random product of independent matrices. That's the point.
I don't think they're independent.
Yeah, sorry.
It's only when you augment the space.
You're right. Right, thank you. Okay, let me say something more about this object appearing here. So we can denote it by sigma s of omega ux, and this gives, I'm just copying this object, us xs, and this is called skew product flow. And it gives kind of connection between the stochastic point of view and the deterministic point of view. Let me put it this way. So here I'm considering the stochastic point of view random dynamical system, and here the deterministic one just deterministic dynamical systems. If we consider a general random RDS, let me denote it tau omega t acting on some space z, satisfying these two properties, or so I mean the important one is the cocycle property. But anyway, let us keep let us take a general RDS operator t. We can associate the skew product flow. This time, the skew product flow is acting on omega times z, and it can be understood as a deterministic flow over the augmented space. And we can consider a linear cocycle over t. And starting from a linear cocycle in this framework, we can build a linear cocycle here. Simply the same object, but now it's acting on the augmented phase space, taking value again in SL2, and this is a linear cocycle in the sense of, I mean, standard sense of dynamical systems. And another interesting point is about stationary measures. So if we consider mu probability over z, which is stationary for the RDS t, and in this random setting, it means that the measure is stationary for the Markov process, but we can see it also in the following way. The expectation of so in average, this measure is preserved. Given a measure stationary in this random sense, we can build in a very simple way by using phi times mu, an invariant measure for the deterministic flow. And if mu is ergodic, then p times mu is ergodic as well. And this is going to be useful. And now I want to stick to this general framework. We consider a general RDST with a linear cocycle, and we consider a stationary ergodic measure over this general RDS, and I'm going to state the multiplicative ergodic theorem and Furstenberg theorem. And after we switch to the concrete setting of Navier-Stokes. Okay, let's start with what we call rigidity step. Okay, given this abstract framework, we are interested in the following limits. Let's start. This is the limit we are interested in, and the multiplicative ergodic theorem ensures as I said, ensures the existence and the fact that the limit is constant. To be a little more precise, what we need is a measure mu, which is stationary and ergodic for our system. So assume mu, which is stationary for our process T and ergodic. And we also need the integrability condition on our family of matrices here. And the integrability condition is the following. We consider the positive part of the logarithm. Consider the size of the matrix A T omega Z. And actually we can consider also the inverse, but let me just write the condition for the cocycle A. Take the logarithm, take the supremum in time, 0.1, take the integral with respect to the invariant measure, and now we have also to take the expected value, because this is a random object, and assume this value. And same condition for the inverse. Under this condition, the limit star exists. Almost the limit star exists. Let me write this way. There exists lambda plus real, such that the limit star is equal to lambda plus for p times mu almost every omega z in capital omega times z. Okay. And so here, the only comment I want to make is the following. The fact that lambda plus is a constant depends on the ergodicity. Without ergodicity, here we will get a function of omega and z. And now the point is that this function should be invariant under the action of these two products. But again, if mu is ergodic, then p times mu is ergodic as well. And by definition of ergodicity, we cannot have non-constant invariant functions. And this gives the constant. So this is the key point. The general statement of the multiplicative ergodic theorem is much longer, and we take into account any direction. But I mean, for the sake of
This is all you need, right?
Sorry.
This is all you need. This about it.
Yeah, that's it depends. I mean, not really. I'm cheating a bit. Yeah, but let us.
One step that means the description of the
spaces,
but
yeah.
Sorry.
Let's cheat a bit. Okay, and now Furstenberg. I need first to introduce the projective process, which is a fundamental process in this business. And let me start by introducing the projective space, which is nothing but R2 minus the origin with this equivalent relation saying that two vectors are equivalent if one is lambda times the other. So essentially, I'm considering the space of one-dimensional linear subspaces of R2, the space of directions, if you want. And we have a very natural action of our RDS in the space Z times P1. And the action is the following. We consider the point Z and an element here, V. So V is a class of vectors. And we just apply our RDS capital T. Let me write it Z of T, which is nothing but T omega Z. And we act on V by means of the linear cocycle. And the action is well defined because the linear cocycle is an invertible matrix, so is a linear action, and the linear action passes to the quotient. Let me just write Vt, and Vt stands for A of T omega Z acting on V, and we should take the equivalence class. And this is again an element of Z times V1. Okay, this is the so-called projective process. Let me now state first and back. I think the version I'm going to state is due to letter P, if I'm not wrong. And this theorem says the following. Again, if we can write lambda plus equal lambda minus, so the biggest and the smallest Lyapunov exponent are equal, or if we want just to consider the biggest Lyapunov exponent, just let's write lambda plus equal 0. Then, and of course, under the assumptions that mu is a stationary ergodic measure for our process T, for our RDS T. Okay, if the biggest Lyapunov exponent is equal to 0, then we can find a family of measures, nu, Z, and Z is an element of capital Z. Those are probability measures. Those are probability measures in the projective space P1. And those are deterministic, not random measure. And the conclusion is that this family is preserved by the action of the linear cocycle in the following sense. Pick A omega T Z. We can consider the push forward. We can consider A as a map of the projective space, as I said, and consider the push forward of the measure nu Z. And this has to be equal to nu of ZT, according to the previous notations. Okay, this is really a deterministic structure preserved by the action of our linear cocycle, and this is true, of course, not for any point. This is true for B. Okay.
So true in high dimensions.
Sorry?
Dimension higher than 2.
Instead, you mean in the cocycle instead of dimension 2 in dimension
2. If it's
yeah, I think it's true with the very same statement.
So it's a
The
general.
dimension is not important, yeah.
As long as it's finite.
Yeah, of course. It needs to be finite. Yeah, let's see what is it. I wanted to give a rough idea of proof, or at least one key identity which may help understanding this theorem, but it's running out. But let me say something about its proof before explaining how to apply it in our setting. I'll be very rough. I will just want to write down a key identity, which maybe helps understanding why we need to consider this projective process. And this key identity is due to Partenberg and Kaminsky. And so here I need to go back to the concrete setting, which is much simpler to present this identity. Z is nothing but H times T2, and small z is nothing but UTXT. And the cocycle again is the differential of the flow map. So in this setting, we have this beautiful inequality. We can bound the biggest Lyapunov exponent in terms of the integral of v x d nu, I think is not a good, anyway, nu tilde. And this is true for any nu tilde probability measure in z times q1, stationary for the projective process. And let me say this way, let us assume that our measure mu, our stationary measure for the Lagrangian process, the process that I call the capital T, is unique. Okay, this makes things easier. And let us pick any stationary measure for the projective process. Then we can always bound lambda plus from below in terms of this integral. And this integral depends on this measure nu tilde. And here we have the gradient of the vector field. And yeah, V is just the integration variable. Now what's the point? Once you have this measure, in order to prove rigidity, you want to show that when this quantity is equal to 0, then some rigidity happens. And so actually you want to prove that when this quantity is equal to 0, you can find the family nu appearing here. And this family is obtained by this integration starting from this nu tilde. So what you can prove is that pick any nu tilde. If this quantity is 0, then you can take the disintegration of nu tilde. Out of this disintegration, you get a family of measures depending on the point in the phase space. And you can show that the identity I wrote here hold by computing the relative entropy of this quantity. Yeah, the relative entropy, how to say it? The entropy. So we start from nu tilde, which depends on z and b, or if you want ux and b. And this can be disintegrated in terms of a family of measure nu z of b, d mu z. And mu z is again the stationary measure for the original RDS. Now we want to prove that this family satisfies the condition in Reifenbeck theorem. And the idea is that this quantity up to a bit of work is actually equivalent to, so this quantity equal to 0 is actually equivalent to the relative entropy of A T omega Z nu Z relative to mu Z itself equal to integrated with respect to mu Z and take the expectation, this is equal to 0. That's how the proof goes. This is not trivial, of course, to pass from this quantity equal to 0 to this other quantity, but I mean, that's how the proof goes. Okay. Now, given this theorem, let me try to explain why it should be at least reasonable that in our setting we can rule out the presence of this deterministic structure. And I want to
think about structures like the new C.
You mean if there is a better
Description or concrete description of it in terms of
I'll give another version of this theorem in a second, in which there is a much cleaner description of what is really invariant. And this new description does not depend on nu Z. So actually it depends on nu Z, but in a little indirect way. So in a couple of minutes, I'll give you another theorem which maybe answered your question. The reason why this structure can be ruled out relies partially in the following simple lemma. Pick two measures, mu and mu prime, probability measure in the projective space, and consider, let me call it H, the set of matrices A in SL2 with the property that A maps mu into P prime. So again, I'm considering A as a function in the projective space. Then you can show that then H has empty interior. This is not really surprising. What I'm saying is that the set of matrices sending this measure to this other measure is actually very small in a sense of empty interior. Now, what's the point? Let us look at the following measure. Qt Z prime. And this is a measure in the space of SL2. And define this measure in the following way. We consider the probability that our cocycle starting from Z belongs to this set K, knowing that at time zero we started from Z, and at time t we reached exactly Z prime. Yeah. Okay, given this lemma, what we know is that the support of this measure has empty interior. So this measure is kind of degenerate.
This is all working under the assumption of lambda being 0.
Yeah, sure. Yeah, assume. Yeah. Let me say precisely. So assume that lambda is equal to 0. We have a Fastenberg conclusion, and Fastenberg conclusion together with this lemma says that the support of this measure has empty interior. Right? Clear?
This now gives some idea of the, and if you consider any process, if the matrices are supporting any set that doesn't have empty interior, then you've immediately ruled out lambda equals 0.
Yeah. This is connected with the density of the so-called matrix process, which is a process obtained by ZT and the cocycle itself. This takes value in Z times SM. So if assume that this process is very regular and densities or Markov kernels are all smooth and positive, then this cannot happen. The fact that the support of this measure is degenerate cannot happen. And here the natural strategy will be, okay, let us try to check that this process is very regular as smooth Markov kernels. And actually in finite dimension, you can do it by means of Hofmann theorem. You can try to check Hofmann condition for this process, and if the condition is satisfied, we are done. And actually this is how the proof goes in the finite dimensional setting of Galerkin, Navier-Stokes or Stokes. The point is that you cannot appeal to Hofmann in the infinite dimensional setting, and this is the main issue that I would like to address maybe after the no, let me continue 10 minutes more. Okay. Okay, are there any questions so far? Okay, very good. Now let us address the infinite dimensional setting.
Okay, so the case you mentioned earlier with the Galerkin, that you would just use Hofmann.
Yeah, exactly. You have to check Hofmann condition.
Be done, right?
Yeah, you have to check Hofmann condition. But I mean, it is possible to check that it's fine.
So the problem is to check Hofmann in this infinite dimensional setting, or to find the analog of Hofmann.
Yeah, or find some strategy to find.
Is this related to what Mattingly and Hire did?
Yeah, this is exactly one of the points I'm gonna mention. Okay, let us try to understand how to rule out the invariant structure in the infinite dimensional setting. Ruling out. So here essentially we have 3 steps. So first is where Hire and Mattingly theorem is used. One has to prove that the Lagrangian process is a strong Feller process. Is strong Feller. And strong Feller means that just means that so if you pick the Markov process associated to this the Markov semigroup associated to this Markov process, and you apply it to any function, you get a continuous and bounded function provided the original function were bounded. So provided bounded. So essentially I'm saying that the semigroup maps bounded functions in continuous and bounded functions. And so if you want, this is a regularity property of the semigroup. And as we have seen for the finite dimensional setting, some regularity has to kick in order to rule out the invariant structure. And here is where
CB means continuous in time and bounded.
Yeah, there's no I mean phi, this is just in space. Okay, let me be a little more precise. So given our process ZT, we can define a Markov semigroup acting on function over Z. So acting on functions over Z. And this is a Markov semigroup. What I'm saying is that if you pick a phi, which is a function from Z to R bounded, then PT of phi is continuous and bounded in Z for any t positive. This is what I wanted to say. Is a regularization property. Good. This is one key step, is where regularity is introduced in the system. And the second step consists in refining first and then we prove the refined version. And let me call it a topological version. And the reason is that one can use Feller to prove that actually the invariant structure is continuous with respect to the parameter z, not only measurable. And this theorem says something more. So we have a more precise description of the invariant structure plus continuity. And once we have this refined version of Fastenberg, we can conclude by means of a controllability argument. Okay, so maybe
What is this controllability?
I'm gonna explain it in the second part.
That's also used in higher.
No, higher is used.
I think they have some controllability issues too. Don't they?
They do.
Yeah, so control. I think controllability is used
But
both.
is that same kind of thing, or because you've got to deal with it. So the noise will take you where you want to go, right?
It's an irreducibility
Yeah.
statement. Yeah. Although this is perhaps weaker in some ways. You don't need to show full irreducibility.
Yeah, maybe in the last 5 minutes, let us assume for a second strong failure, and I'll say actually very little later how the proof works. Let me state the refined version of Fastenberg. So the first observation, which is actually highly non-trivial, is that let us assume again lambda plus equal to 0 and consider the family of invariant measure mu z. Okay, let us stick to the general setting. There is no necessity to consider the concrete one. And if we assume that the process is failure, so if our process is strong failure. So first, we can prove that the family nu z up to a small modification is actually continuous with respect to the parameter z. This is continuous with respect to the width topology of measure. And so at this point, we can make the following observation. This is a highly non-trivial step. It's a very fundamental step. Once we have that, we can make the following observation. We can use the structure of compact.
Is that abstract statement? If I have strong failure, it is abstract.
I think maybe here you use a bit the concrete structure.
No, it's abstract in the sense that if you have this invariance and strong failure, then you can prove that they have to be continuous. This is one thing that don't know how to prove, or is not clear if it's true in a weaker asymptotic strong failure setting, which is why we have to force all modes.
I see. Yeah.
This is like one of the key points where it fails with weaker modes.
That's why you need strong stochastic.
Strong failure.
Yeah, you need strong stochastic input, right? To make sure everything moves.
So okay, now we want to use the structure of subgroups of SL2 plus this continuity. Get a refined version of Reifenberg. And the structure property we need is more or less the following. Let me introduce the following subgroup of SL2. Pick any Z and consider the subset of matrices mapping nu Z, and again nu Z is one of these measures into itself. It's not hard to see that HZ is a compact subgroup of matrices. Is a closed subgroup of matrices, not necessarily compact. It's a closed subgroup of matrices. But now we have continuity in Z. So this family of subgroups changes continuously. So in particular, either all subgroups are compact or all are non-compact. the two different cases. Compact. So in this case, the picture is very simple. Essentially, compact subgroups of SL2 are subgroup of rotations, essentially. And what I mean is that we can always find, given H, you can always find a scalar product in the Euclidean space depending on H, such that any element of H is an isometry with respect to the scalar product. Such that let's write A, B.
Just use the Haar measure.
Yeah, and this can be done just by considering the Haar measure here and integrating against the averaging, averaging with respect to this Haar measure. And this gives the metric. Now we have the second, this is pretty simple. We have a second case, which is the non-compact case. And so in this case, the picture is slightly different. So essentially we get subspaces and a family of subspaces, and any element of H acts as a permutation in this family of subspaces. And a very simple example to keep in mind here is the following. We can consider, for instance, the group given by lambda 0, 0, 1 over lambda, 0, mu, minus 1 over mu, 0, where lambda and mu are equal. This is a subgroup, and we have two different type of matrices. This one which is diagonal, and this other.
It's a subgroup generated by them?
I think it's automatically, if I'm not wrong. If you take the product.
You did the product.
I mean, I'm just trying to understand what the group
No,
is.
it's a bigger, I mean, it's
It's a group generated by.
No, it should be all those actually, yeah, because
I think it's already a group, right?
it's just two, more or less two.
So if I multiply two of those, I get something that looks like that?
Yeah.
Okay.
Yeah,
Yeah.
you just get another hyperbolic one or a
Okay.
rotation.
Yeah.
At least.
Yeah, I computed it starting
Yeah.
from one of the measures, so it should be. Now, what's the point? The family of subspaces are simply the one generated by the first element of the canonic base, and the one generated by the second element of the canonic base. And the first, so this matrix acts by simply keeping both fixed, while the second matrix acts by swapping the two. And this is a general picture. So in general, you find the number of subspaces and the action is a permutation, and the permutation depends on the matrix itself. That's it. Given this result, I can finally write down the version of Furstenberg. And yeah, it says the following. So again, assume Stromfeller and lambda plus equal to 0. Then we have two alternatives. One, which corresponds to the compact case. We can find a family of scalar products depending on Z, such that the scalar product of our cocycle, our linear cocycle, is preserved. If we consider the scalar product, let us consider two vector fields, two vectors V and W, and let us apply the linear cocycle to V, the linear cocycle to Y. We compute the scalar product, and this is equal to V times W Z T. And now the conclusion is a topological one. This is true for any Z, omega, V, W, and T. And moreover, this family this family varies in a continuous way. So this is a continuous map. And the second point corresponds to the non-compact case. And it says the following: we can find L1Z, E1Z, EPZ. Those are linear subspaces of R2, depending on Z, and again, this family is continuous with respect to the parameter Z, and the linear cycle acts as a permutation.
Their union and variant.
Yeah, and the union
What's the same?
is also important condition. If you pick the union of these spaces, and the new measure is equal to 1. So they cover everything according to the new Z measure. Okay, so either rotations or permutation of subspaces. And yeah, after the tea break, I'm going to show how to rule out these two possibilities.
How to do what?
There's no parabolic case.
Sorry?
There's no parabolic case.
Uh,
I mean, if I think of the first one as kind of rotation,
yeah.
the next one is hyperbolic. There's no
Yeah.
single linears of one low and something.
No, that's a good point. I'm not sure why that doesn't. I mean, that doesn't even show up somehow in Furstenberg's.
But that's weird, right?
It is true. It somehow doesn't allow for that. Yeah, that's a good point. I don't really know why that doesn't show up naturally. Essentially, if you have, the second you know that thing has any parabolic behavior, it rules out the first one. Which, I mean, there's sort of this interesting thing that if you know that these measures are absolutely continuous, then even parabolic behavior rules out lambda equals 0.
Oh, so maybe it's contained in a non-compact case, right? Parabolic behavior.
Oh, that's true. I get any unboundedness is contained. Yeah, that's right. Yeah.
Let's stop here.